Section 7.3 is a section that I won't assess you on, but I think is one it's good for us to look at. And it's ways of checking for normality. It really answers the question, is my data normal? The answer to that question is not very simple though, and there are quite a few different ways of assessing normality. Also, within each of the ways of assessing normality, there are variations. So it's something that's not very much agreed upon within the world of statistics. And we're going to go through a few different ones, and I'll explain how the technology is programmed. Just to give you an idea of ways that you can check for normality, if you would look it up on Google or anything, there are lots of different ways of assessing normality, and they sometimes can be very confusing. So normality describes whether data follows a normal distribution, and there are many different ways, just what I said before. One way is that you could just make a histogram and see if it looks bell-shaped. This is a little bit subjective, so maybe not the greatest way to do it, but it is one way to look at the data. Also, you could check for outliers. You could use the fences as checks for that. You could make a box and whisker plot and kind of see visually if there's an outlier. Outliers may skew the data too much for it to be considered normal. There's another thing that measures the skewness. It's called Pearson's index. And if it's less than -1, it's too skewed to the left. If it's more than +1, it's too skewed to the right. The formula for that Pearson's index is right here. It's 3 times the mean minus the median, and then you divide by the standard deviation. The last one that we're going to look in more detail about is called a normal quantile plot. There are a bunch of different names out there for these as well. QQ plots are like a variation. And what they do is they take the data, they let that be y, and then the quantile, which is a z-score corresponding to, it's not even like a percentile, it's kind of, so you think of like the quantile as a more fluid percentile. So like a percentile splits it into by percentages 1 through 100. Quantiles could split it into any number of equal regions, and that value that goes along with the data, it should form a straight line. And so we look at a linear regression of those data values and the quantiles that we compute and see if it falls within a straight enough line. And if it does, then we'll say that it is normal. And if it doesn't, then we'll say it's not normal. Now, within the normal quantile plots, lots of variations, lots of different ways to compute quantiles, or even like the spacing between the two, and it gets pretty complicated. So what we're going to use is the checking for normality Excel file, which I created. Took me a lot of time to create. And what you do, you paste the data into column A, and then also make sure it's from least to greatest, just like descriptive statistics. Do that sort A to Z, make sure it's in order. The Pearson index is calculated for us, and we could use that as well. The correlation coefficient for the normal quantile plot is calculated in cell D13. And if this value is larger than the critical value, which is in cell D14, it's approximately normal. Okay, so the example here, I'm just going to show you one example. There's a couple in the homework, but not very much in the homework, and just let me know if you're running into difficulty with those. Use the checking for normality Excel file to check to see if the height data is normally distributed. So we would think, okay, height, yeah, it should be normally distributed, but let's just check it. So I have the data file here, and it's just a bunch of heights. There's, I think, 48 heights. So I'm going to highlight these, and I need them to be in order from least to greatest. So the first thing I'm going to do is sort that from least to greatest in this file here, which is good. Now I can copy and paste it into the checking for normality. So I'm going to open up our course and go to the Excel files, and checking for normality is the one we want to use. So I'll download that. And I'm going to paste it within here. Paste just those values in there. And once you do that, you can really just leave this other stuff alone. It creates a histogram over here. So it looks kind of mound-shaped. Pearson index is getting close to 1, but it's not quite too skewed. So I must have had someone that was extra tall. Yeah, a couple people who were pretty tall. And the two things that we want to look at here, this is the correlation coefficient of the normal quantile. This one is greater than the approximate critical value. And because of that, we would say, okay, it is approximately normal, where it came from a population distribution that is normal. We can see the quantile plot down here. Scroll down a little bit further. It says what it looks like. So the more this is in a straight line, the more normal it is. Okay, now just to point out a couple details, here's the quantiles. Blom's plotting position, this is just what is used in the book. There's lots of other plotting positions that could be used. That's the formula there. I put that just in case anyone is interested, which you probably aren't. The critical values actually come from this one academic paper, and Looney and Gullidge were co-authors on that paper. I just copied them in here, and then you have to approximate for certain values, which I did here. This only works for data up to 100 data points. I think I have, oh, I put more here. Yeah, this critical value might, they do go higher, but I didn't put those values there. Anyway, for the homework, you only have data, it's like 20-30 data points that you'll use in the homework, but this wouldn't work for higher or bigger data sets. But yeah, an interesting question to answer for sure. Not an easy question to answer. Lots of different ways to answer if something is from a normal distribution.